Hello, biostatisticians. So today we're going to continue with hypothesis testing. We started this on Tuesday. We covered a good majority of what we needed to. We talked about setting up your step 0, which is finding what is given in the problem, such as alpha, your sample size, your population mean, or maybe even your sample mean, your population standard deviation, or maybe even your sample standard deviation. So that's what we'll kind of do here. We'll go through that step, and then we went on to step 1. We found a null hypothesis, usually something from a previously known fact or study, usually given in the problem. And so far we've just been talking about mu, so whatever mu is really is going to be the null hypothesis. The alternative hypothesis, which can be less than, greater than, or not equal to, correlating with left-tailed, right-tailed, or two-tailed, respectively, in the order I said it. Also, we'll talk about finding a critical value. So from your problems, from using your alpha, you'll be able to find a critical value, which actually is mainly from the first notes from Tuesday. I'll talk about it today, but I showed you how to use the inverse norm, and then today you'll kind of use inverse t. However, I won't be showing calculator steps. I will kind of narrate them, and you can kind of follow through with those. So also we have test statistics that we compare, right? So the main idea, I'll kind of just draw up here, is we have some null hypothesis, right? And then we calculate an x bar in this case, and we calculated the z-score. Actually, before that, we find some critical value that we determine. So this would be z critical. And we determine, okay, this is the cutoff point to where we no longer believe the null hypothesis is true, and anything beyond this point, we would say that the alternative hypothesis, or we have evidence to suggest the alternative hypothesis. So in this region, excuse me, in this region would be what we call the critical region. Okay, and so far all I've showed you was if you calculate z-test in this critical region, then you reject H0, and if it's not in the critical region, you fail to reject H0. Okay, which is on some slides in the previous in what we did on Tuesday. Okay, all right. So with that said, that's kind of the main idea. We're going to jump into a specific problem. I think the more you kind of see them, the better you'll kind of understand it. So for a specific year, the average score on the SAT math test was 515. The variable is normally distributed, and the population standard deviation is 100. The same superintendent in the previous example wishes to see if her students scored significantly below the national average on the test. She randomly selected 36 student scores as shown. At an alpha of 0.10, is there enough evidence to support the claim? So then you have all those numbers, but before that, let's just talk about what is given on this problem. Okay, so I like to call this my my step 0. And actually, before I start, I would say that your textbook does have different steps. I think up to 8 steps, but actually the steps that I kind of do encompass all those 8 steps. So the step 0 through 5 that we talk about in here encompass all the steps 1 through 8 in there. So for instance, maybe I don't really make a step out of finding alpha. In fact, I put that in my step 0. So that's a step in your text. So you might notice that discrepancy in your MyMathLab homework. Okay, but again, all those steps are kind of encompassed in my 5 steps, and that's kind of what I look for is the 5 steps when I'm doing not multiple choice questions, but free response questions. Okay, so you'll have to kind of adjust for your MyMathLab homework, but all the information's there. So I'm going to go, actually let me call this step 0. Let's write a little less. So step 0 is just point out anything that you see in the problem. So here I see the mean is given as 515. Also, they give you the standard deviation. You got to always think, is it population or not? In this case, it is population standard deviation because it tells us. They also give us alpha is 0.1. Okay, and they did a sample of, it looks like 6 by 6, so 36, but it also tells us in the problem, so that's n is 36. Other than that, they don't give me anything else. However, you do have a list of data, so what can you do with that? You can go ahead and put that in your calculator. So you would do stat, edit, and then you take some time to enter that in. I won't do that here since you can't really see my screen either way. So we'll just, I'll leave that for you to look at. Then you would do stat calculate, and you can see the X bar. So from there, if we, I would get the X bar. I'm gonna go ahead and write those down. X bar turns out to be 509.028. Okay, so this we'll use a little later. Okay, all right. So far so good. Our step 0 is done. Okay, so we're gonna move on. We're gonna do now our hypothesis test. So the first step, which I'm noticing right now on your slide, step 1, it says find the critical value. It should say hypotheses, because step 2 would be find the critical value. Okay, so hypotheses. So we would want a null hypothesis. In this case, I told you in class, don't think too hard. The null hypothesis is basically going to be, in this case, all we're dealing with is mean. But when we deal with proportions, you'll put p. Right now, it's just going to be the same thing as your population parameter that we're studying, with the alternative being that in this case, if we go back to the problem, we read it, it's either going to be less than, greater than, or not equal to. So if you look at the problem, you see the sentence, the same superintendent in the previous example wishes to see if her students scored significantly below. What does that tell you? That's right, less than. Okay, and then you ask yourself, is this a left-tailed, right-tailed, or two-tailed test? It's a left-tailed. Why is it a left-tailed? Because it's less than. So in this step, I usually like to define what mu is. So you would say something like, where mu is the true population mean SAT score. For students in the superintendent's district. Okay, and that would be your that would be your definition of what mu is. So every time we refer to mu now, this is what it means. Okay, so that's important. Okay, so that's the end of the hypothesis step. So step 2, we would want to go ahead and find our critical value. Okay, and in fact, I'm going to go ahead and I'm going to do something here. I'm going to change these to red. Okay, so let me do that. Okay, ta-da, the red. Okay, so critical value. So this we talked about in class, and maybe it's worth another mention. You know, one more time. I'll take an aside here, but there's, and I'm going to erase this, so you don't need to write this on this part of it, because this is not with respect to this question. This is more in general. So again, you have a left tail that's a less than, a right tail that's a greater than, a two tail that's a not equals to, alternative hypothesis. Of course, this one's a left tailed, but in general, for all these, you're going to have to use inverse norm to find your z critical. Okay, to find your z critical. Now the difference is what will you use for the area. In this case, if that's alpha, your area you're going to use as alpha in your calculator, right? And then that'll get you your z critical. Over here, now this is alpha, so the area you'd use is 1 minus alpha. Okay, because the calculator only gives you area to the left for most of your calculators. Now this one, both combined are alpha, and then so this side would be alpha over 2. So then your area that you would want to use, or one way you can do this, is using alpha over 2. And then you'll find your z critical for this, and then which makes positive z critical this. Remember, that's going to be 2 answers, so that'll be a negative, and then you just make it positive, you got the other side. So this is very important for the critical value step. So I'm going to erase that now, but for some reason, I tell you all that in class that students find that the most challenging, but basically it's just inverse norm. Area to the left, it's just alpha, area to the right, it's 1 minus alpha, area on both sides, alpha over 2. Okay, so now using that, and I'll write the calculator steps, usually I don't, but so here, inverse norm, area, so this is for z critical, inverse norm area equals to, well, what was our alpha? And I would also draw a picture here at this point, so let me do that. So our alpha is a left-tailed test. That kind of helps me here to remember this. That just tells me I'm going to put alpha right there, which alpha in this case is 0.1. Okay, so I would just input that into your calculator, and then you'd get an answer there. Okay, so when I do it, I end up getting my z critical. I'm going to put it right here. Z critical equals to negative 1.28. Okay, so that's my cutoff of when I'll believe that it's not going to be my null hypothesis, mu of 515. Okay, so that's what we discovered. So the next step. Oh, actually, one thing I was going to mention. It might be good for you to try these. You know, maybe pause the video, see if you can get these numbers. Okay, because that's kind of like we do in class. If you do it, you're bound to remember it a little bit better. Okay, so step 3, we're going to go ahead and calculate the test value. And if you recall, our test value here will be z equals x bar minus mu divided by the standard deviation over the square root of n. Okay, and this comes directly from our previous section. Okay, so if I input this, I'm going to get, we know x bar is 509. Remember, that's what we did from our list of data, and we put it in the calculator and did 1 bar stats, minus 515 over the standard deviation of 100 divided by the square root of 36. Input that into a calculator, and you're going to get 478.128. Okay, so that's, well, actually, let me double check that, and I think that might be off. Okay, actually, yeah, this is much better. Negative 0.358. Negative 0.358. Yeah, and 478 is kind of high. Remember that 3 standard deviation contains most of the data. So, although it's not impossible, but yeah, you want to check your work if that happens. Also, I knew too, because this is below the mean, therefore it should be a negative standard deviation, because it's going to be that many standard deviations below the mean. That's what a z-score means. So always good to know these other things to check yourself. All right, so step 4, we're going to go ahead and look at that, and that's going to be make the decision, right? So now we have z-test, and usually I write z-test here. You should too, because there's 2 z-scores, not to confuse z-test with z-critical. So now we're going to place this in here and decide, is it in the critical region? Well, negative 0.358 is going to be somewhere around here. So therefore, it is not in the critical region. So we're going to make conclusions. So step 4, we will say since z-test is in the critical region, or non-critical region, we fail to reject H0. Okay, fail to reject H0. And usually I like to just restate it, that the mean SAT score is less than 515, or equal to 515. The null hypothesis. Okay, so that's a good conclusion on the null, and then usually on step 5, what I like to do is make a statement about the alternative, H1. So usually the conclusion I'll say about H0, the statement I'll say something about H1, which we don't want to say anything conclusive or 100%. We just want to say what we have evidence. So in other words, there's evidence to suggest H1 is true, that, and then I'd like to restate basically what it means, that the mean SAT score is less than 515. Okay, so see, that's so people wonder about letters. Well, really the letters are about being a little bit lazier, not having to say that that's the mean SAT score less than 515, because a lot of times you're writing papers and you'll be referencing that because that's what you studied maybe 30 times. So instead of writing this 30 times, you write it one time, and every time after that you refer to it as mu. So that's part of the reasoning. Okay, so this is kind of a complete hypothesis step. Step 1, we wrote the hypothesis. Step 2, we did the critical value using the inverse norm. Step 3, we found the test value using the formula. We'll have some different formulas coming up. And then step 4, based on the test statistic, if it fell in the non-critical region, we either fail to reject or reject if it's in the critical region. In this case, it was a non-critical region, so we failed to reject H0, that the mean was 515. From there, we after we made our statement about the null, that we failed to reject it, there is evidence to suggest that H1 is not true, actually. Not true. Yeah, okay, so some of y'all were waiting for that, right? Why don't you tell me these things? So there's evidence to suggest H1 is not true, that the mean is less than 515, because we failed to reject H0. So that means there's no evidence. Okay, and I can restate it too. There is no evidence to suggest H1. Yeah, we can say that. In fact, I like that better. There's no evidence. There is no evidence. Okay. All right. So that kind of finishes up that question. I'm kind of thinking maybe I can explain another thing with this. Yeah, let me think. Yeah, you know what? It's set up. So I'm gonna go ahead and show you this other idea So there's two methods of doing the same thing. One is what we have here is the test statistic method. So the test value. So we do the hypothesis test using a test value. Now I want you to understand something. So here's Z critical. The area beyond Z critical you already know is alpha, right? Which is a type 1 error. Now there's another area, okay, here, which is called Z test, which is everything beyond, the area beyond Z test, okay? This area, which includes this red and then red and black right here from alpha, in this particular problem, this area we're going to call everything beyond that, it's called the p-value. Okay, so there's an alternate method, and I don't think I'll write it because it's coming in a couple of slides. In fact, I can reference you to the slide. With slide 47, it says if the p-value is less than or equal to alpha, reject the null hypothesis. If the p-value is greater than or equal to alpha, do not reject the null hypothesis. So here, what does it look like? The p-value is in red, alpha is in black. Is the p-value less than or greater than alpha? Well, clearly the p-value would be greater than alpha. So according to that slide 47, if p-value is greater than alpha, do not reject the null hypothesis, or in other words, fail to reject the null hypothesis, which is what we did, right? Which is what we did. So, so I guess the takeaway here is you should know that Z-test helps you calculate the p-value. In fact, let's go ahead and calculate the p-value here because you should know how to do this. Okay, although I understand if you wouldn't remember, but you're going to have to remember for upcoming work we're going to do. So here it's normal CDF. So we're going to do normal CDF from, and I'll write it actually. So we're going to do normal CDF from lower bound is going to be your negative infinity, right? Negative infinity to upper is negative 0.358. Okay, and then the mean, we're going to leave it at the standard normal curve because we have a z-score. Then you calculate, right? So I'll put that in, negative 0.35801. And I get 0.3601. 01. Which tells me that the p, in other words, the p-value. So if I were to do this a second alternate way, all this would say, all that would change would be my step 4. None of the previous steps would change other than I would write the p-value in place of on step 3. Okay, so this is coming up, right? Because you might be asked, solve using the critical value method or solve using the p-value method, which they're almost exactly the same except for the test value. You're going to find the p-value, okay, using normal CDF. But we're going to do more on that, so don't worry. So the step 4 here would say, instead of saying since the z-test is in the non-critical region, we would say since the p-value is greater than alpha, we fail to reject H naught. And then actually step 5 would not change, right? The reasoning here is the only thing that changes, and also the fact that instead of the test value you just have the p-value there. So step 5 would just be step 5 would be same as up there. There's nothing different. Okay, all right, so that's just to kind of give you a jump ahead on the next problem since I had it here ready, but let's go ahead and get into the next problem. So this one's about rehab, so I'm going to go ahead and read it on slide 42. It says the Medical Rehabilitation Education Foundation reports that the average cost of rehabilitation for stroke victims is $24,672. To see if the average cost of rehabilitation is different at a particular hospital, a researcher selects a random sample of 35 stroke victims at the hospital and finds the average cost of the rehabilitation is 26,343. The standard deviation of the population is 3,251. At alpha equal to 0.01, can it be concluded that the average cost of the stroke rehabilitation at a particular hospital is different from 24,672? Okay, so first I'm going to erase the board, okay? Okay, it's erased. So now we're going to go ahead and do find our step 0, which is what's given. So you look through the problem, underline, and then you write down stuff. This I think is very helpful. I wouldn't skip this step. It just definitely helps things flow a lot better if you get it down one time. So the mean is going to be, so they give us the 24,672 as the average cost of rehabilitation for stroke victims. So as previously reported. So that's going to be our population mean, okay, from previously reported research, or our assumption, right, the null hypothesis. So here they also give us 35 stroke victims, a random sample of 35 stroke victims, so that's our sample size. From there they found that the average cost of rehabilitation for a stroke victim is 26,346 or 43. Okay, and following that, here we go. And do they give us anything else? We do have a standard deviation population 3,251. Okay, so they did give us a population standard deviation. That's a good indicator. We're going to use a Z and not T, which is coming. But okay, let's jump into the hypothesis. So here, again, I tell you, don't think too hard. Your hypothesis is basically going to be your population parameter, mu. Okay, so mu equals 24,672. That's going to be our null. Our alternative is going to be mu, and remember that's going to be the same number. And then we want to determine less than, greater than, or not equal to. So it says on this problem that can it be concluded that the average cost of stroke victim at a particular hospital is different? Different. So different meaning not equal to. Okay. So this is a what? A left-tailed, right-tailed, or a two-tailed test? Well, if it's not equal to, it's going to be a two-tailed test. So I like drawing the picture here, and since I know it's not equal, I'll just go ahead and draw my two tails, shade it to the left, shade it to the right. Both together are alpha, so each individually is alpha over 2. And from our, well, that's what we didn't get. Our alpha is 0.01, right? Okay. From the problem, and then alpha over 2 would be 0.005, right? So again, I'll write it. Inverse norm is to calculate our z critical is going to give us area of alpha over 2 because it's two-tailed, and mean of 0, standard deviation 1, but I'm not going to write that. So once I calculate that, I'll end up with negative 2.58. So that's my, I'll put my z critical right here. Negative 2.58, but also positive 2.58, because on a two-tailed there's going to be two critical values, and anything that goes beyond those critical values, that's going to be in the critical region. Therefore we'd reject the null, and if not, we fail to reject. So the test value is going to be the same. It'll be z equals x bar minus mu divided by the standard deviation over the square root of n. Okay, so you just plug in stuff. All right, calculate x bar 26,343 minus mu 24,672 over population standard deviation 3,251 divided by the square root of 35. Okay, Input that into your calculator and then you'll get an answer. Okay, which I get 3.04. Okay, so then that's the test value. So then now it's time to decide. Using this test value, the z-test, right? And I did it again. I'd like to make sure that I write z-test to distinguish between z-critical and z-test because they're two z-scores. When I didn't do that, students got real confused. Okay, but if you do it every time, it should make a lot of sense. So here I have my z-criticals. I'm going to place z-test, which is going to be, since this is 2.58, 3.04, must be somewhere out here. So that's my z-test. And then we can make a decision. What's our decision? Are we going to reject the null or fail to reject the null? Well, we would say something like, since z-test is in the critical region, we reject H naught. And then a little statement about H naught, that the mean, oh, and I just reminded myself, maybe y'all picked up on it. Okay, but you didn't tell me again. We didn't define it. So this is important. You gotta define it once. Where mu is the true population mean cost of rehabilitation for stroke victims. Okay, there, that's what mu is. Okay, all right, so good. From there, we made a statement about the null. We want to make a statement about the alternative. So if we reject H naught, is that evidence to suggest the alternative or not? Well, if we're rejecting H naught, that does give us evidence to suggest the alternative. There is evidence to suggest H1 is true. And then again, I'd like to put a little excerpt that the mean cost of rehabilitation for a stroke patient is not equal to 24,672. Again, I'm not claiming that it's less than or greater than. I'm just saying that we have evidence to suggest it. Okay. Okay. So let's do a little more. So that's that. But let me reiterate another point here. So this is the critical value method, right? In a little bit, we'll do a purely p-value method. But so remember, I said the p-value is the area beyond z-test. So in this problem, my area beyond z-test is here. Okay. So this in red is the p-value. Okay, and then so what in compared to alpha over 2 actually, so this one could be a little bit tricky because you actually have to do, the p-value would actually be the area beyond this, but not only do you have to do the positive z-test, you would have to do the negative z-test. Okay, so basically do normal CDF and then just times by 2 to compare it to alpha, but to get the true, so that would also be the p-value. In fact, I should probably say that's the p-value over 2. Okay, but yeah, not necessary. So the two areas are the p-value. Okay, let's put it that way. The two areas in red are the p-value. Okay, so then I would do normal CDF. So I'm going to do that, second varse, normal CDF from 2.58 to infinity, E99, and I end up with 0.005. Okay, but like I told you, so p-value equals 2 times 0.005, right? Because if I do normal CDF from 2.58 to infinity, I get 0.005, but times two sides, that's going to give us 0.01. Okay, now what was alpha? Well, okay, I'm going to have to be more stringent here, because alpha, let me use more decimals here, 0.0, and this one's going to be an interesting one because it just cuts it. Let me check something real quick. Okay, actually, yeah, after checking my my work there, the p-value from 3.04, the test statistic, right, the test value, from the test value on to infinity, that's 0.0012. That's one side, 0.0012. Multiply that by 2, you get 0.0024. That's the p-value, okay? But that you only multiply by 2 on a two-tailed test. On a left-tailed or right-tailed, it's just whatever the area is. Then from there, is this p-value less than or greater than alpha? Well, clearly it's less than. So your alternative way of doing this would be step 4. Well, this would kind of substitute well, really it substitutes your critical value step, and then your test value step moves up one. But your step 4 basically would be the same conclusion, different explanation. So you would say something like, since the p-value is less than alpha, we reject H naught that the mean equals 2,400 or 24,672. Okay. Also, you would just say that step 5 would be same. There's nothing different about that. Okay. So really the only difference between this one is on the p-value step, you don't actually need to calculate the critical value, so that's good. You still need to calculate z-test, but then after z-test you get the p-value. So it's almost the same amount of work either way. I'm just showing you both in one and how they relate to each other, but they're equivalent. Okay, so whatever you get for one test using the p-value method, it's the same. Should be the same solution for the critical value method. Okay, so it's just a matter of preference. But speaking of preference, so what's more used in the real world is actually the p-value method. You'll see that more often in research papers. Okay, so let's keep trucking along. We finished that one, the cost of rehabilitation. And now on page 46, you'll see a little bit what I'm talking about. It says the p-value. So let's actually talk about what it means. So the p-value is the probability of getting a sample statistic, such as the mean, or a more extreme sample statistic in the direction of the alternative hypothesis when the null hypothesis is true. So again, what's our null hypothesis on this problem? We're going to assume that what the previous study said were true, that the mean cost of rehabilitation is 24,672. Under that assumption, with that standard deviation as well, I'm going to take a sample. We took a sample at 35, and then from that sample at 35, we ended up with 26,343, which is greater than this. But is that greater than 24,672 enough to say that it's truly different, or in other words, statistically different? So what they come up with was, okay, we're going to standardize it. We'll make a z-test, and then we'll see how many standard deviations it is above, which is 3.04. And then if that goes beyond our cutoff, then we're going to go ahead and say it's safe to say that the mean is no longer 24,672, but in fact it's not that. Okay, the mean is something else. Okay, so that's all we're proving, or gaining evidence for. So that's kind of the idea. So in other words, the p-value is the probability that you would get your sample statistic given that the null hypothesis is true. Okay, which that probability here is the chance of you getting this being that the null hypothesis is true is about 2%. or 0.2%. So meaning it's a very low chance that you would get this, given that your your mean is actually 24,672, giving me evidence to suggest that, okay, it's probably not 24,672. All right. And then the next slide just kind of tells you what I pointed out earlier. That's the one I pointed out to you, 47, slide 47. It says if the p-value is less than alpha, less than or equal to alpha, reject the null hypothesis. And if the p-value is greater than alpha, do not reject the null hypothesis. So you might want to store that slide and come back to that. So now we're going to do the p-value method, which is I'm on slide 48. And under this slide, you'll notice you'll see a lot of the same steps. And I like step 0, right? Put your key facts and your givens. Step 1 would be state the hypothesis and identify the claim. That doesn't change. Step 2 is compute the test value, which was step 3 previously. Step 3 now is once you compute the test value, right? You're going to use normal CDF and compute the p-value. That's all there is. That would be my point of emphasis on this. I think the rest you can kind of gather, but for some reason or other, students forget to use the normal PDF or normal CDF correctly. So really focus on how to calculate the p-value using the test statistic. And remember, there's 3. There's a right-tailed, and the left-tailed, and the two-tailed. But the one that's most troublesome, I think, is the one we just did, which is a two-tailed test. But really, as long as you remember, you're going to do kind of from z-test on, but you got to multiply it by 2. Okay, multiply by 2 for a two-tailed only. So that's step 3. Step 4 is make the decision. You can use the previous slide to remind you of what the decision would be. If the p-value is less than alpha, you reject the null hypothesis, less than or equal to alpha. If the p-value is greater than alpha, do not reject the null hypothesis. Okay, so like I usually say, it's usually just best to jump into an example, so that's what we're going to do. So let me erase this again, okay? Okay, so we're going to go ahead and read the problem. So this one's about cost of college tuition. It says a researcher wishes to test the claim that the average cost of tuition and fees at a 4-year public college is greater than $5,700. She selects a random sample of 36 4-year public colleges and finds the mean to be 59,050. The population standard deviation is 659. Is there evidence to support the claim at alpha equal to 0.05? Use the p-value method. Okay, so again, I like to do a step 0, which my step 0 is basically just kind of list out anything that we feel like is important along with their symbols. What I see is I just kind of go from the top. He tests the claim that the average cost of tuition and fees at a 4-year college is greater than $5,700. Okay, so if that's what we're testing, that's going to be our mean, our assumed mean, 5,700. I see n equals 36. I see from that sample of 36, they got a population, or they got a sample average of 5,950. Okay, and then from there, they use the population standard deviation, so you make sure you use that symbol, not S, and that was 659. This time we won't forget alpha, it's 0.05, and then from there, I think we can go ahead and get started with our step 1, which is find your hypotheses. Okay, so the hypotheses is going to be that, again, I always I tell you this, don't think too hard. There it is, right? That's why step 0 is important. Now the alternative, that's going to be the same number. Now I got to go back to the problem and read to see if that's going to be less than, greater than, or not equal to. So is there evidence to support the claim? And then if you go back to the very first statement, it says a researcher wishes to test the claim that the average cost of tuition and fees at a 4-year public college is greater than 5,700. Okay, so I think it's going to be greater than, right? Why? Because it says so. This time we won't forget as well where mu is the true population mean cost of college tuition. Okay, so again, we recorded once. We have it for the rest of our paper, and we can just refer to the mean cost of college tuition as mu. Okay, so that's step 1. Step 2, we want to compute the test value, right? So again, let me just key you off on this, kind of getting you ready for what's coming. But we're given the population standard deviation, okay? So keep in mind, we are now doing the p-value method. This is why we're doing test value as step 2 now, using the p-value method, not the critical value method, which is the previous examples. But you'll see that a lot of it's the same. So here we're going to calculate our test value on this step. Okay, so here x bar is 5,950 minus mu is 5,700 over standard deviation is 659 divided by the square root of 36. Calculate that and we'll end up getting our z test. Don't forget to write that. Z test. Okay, so you didn't put it into a calculator. Okay, so I end up with 2.28 as my score. And then from here, what I would now do is we're going to move on to step 3, which is going to be using what we just found. We want to find the p-value. Okay, so this is where I would draw my picture under the p-value method. Okay, so my p-value, I would place my z-test somewhere, which is here, about here, 2.28, and then if that's z-test, okay, what I'd like to do is calculate the p-value, right? So how am I going to do the p-value? Normal CDF, right? So second bars, normal CDF of 2.28 to infinity, paste 0.0113. 0.0113 is what I end up getting. So here, 0.0113. That's the area beyond z-test. Okay, so you got to remember z-test goes with p-value. Although we're not doing z-critical right now, but z-critical goes with alpha. Okay, those are important. Okay, so now we have the p-value. Now we're ready. We're ready for the conclusion. So step 3, or step 4 actually, would be conclusion. All based on H naught. So we would say something like, since the p-value is, well, okay, how about I write it this way? Since the p-value is what? Compared to alpha. Our p-value is 0.0113, alpha is 0.05, so less than or greater than, obviously less than alpha, therefore, since the p-value is less than alpha, based on that slide, I think it was 47, therefore we reject H naught. Okay, and again, if I were to draw alpha in here, alpha would be, so now we're comparing areas, right? So alpha's area would be 0.05 versus the p-value would be 0.0113. Whereas before we were comparing position of the z's. z-test versus z-critical, right? Positions, but now we're comparing areas, which turns out to be equivalent. Again, why? Because z-test goes with p-value and z-critical goes with alpha. So the two tests are equivalent. So we're done with step 4. So now we're going to move on to step 5, which is make a statement about H1. And the statement would just be, since we reject H naught, there is evidence to suggest H1 that the mean is greater than 5,700. Okay, so that's how you do a write-up for hypothesis testing for the p-value. Okay, so that should get you through that slide here. And then we got a few more. It's pretty much kind of the similar stuff, but we're gonna keep talking about it because little things change. But let me go ahead and erase this. Okay, so this one's about wind speed. A researcher claims that the average wind speed in a certain city is 8 miles per hour. A sample of 32 days has an average wind speed of 8.2 miles per hour. The standard deviation of the population is 0.6 miles per hour. At alpha equal to 0.05, is there enough evidence to reject the claim? Use the p-value method. Okay, so we're going to continue with the p-value method. So first things first, step 0, write down what we know. So it says that the claim is that the average wind speed in a certain city is 8 miles per hour. So I'm going to put that as my mu. Also a sample of 32 days, that would be n, my sample size. And it also says that we want, with the mean, that sample was 8.2 miles per hour. 0.2 miles per hour. The standard deviation of the population is 0.6. So we're given population standard deviation with an alpha of 0.05. Okay, so that's our step 0. We lay down all the facts that we have, and then we'll jump into the null hypothesis. Again, I keep telling you, don't think too hard. What I did notice while I was erasing, let me mention this, I failed to put null. All I put was the mu. Don't do that. Okay, make sure you write the null hypothesis. So go back and correct that in alternative. Okay, and you know, at any point in the video, if you feel like something's going a little fast, well, that's why it's good that it's video, right? You can pause it and rewind it. So here, the mean is equal to 8. So if I want the alternative, I know the alternative is going to be mean and 8. And I just got to determine, is it less than or greater than. So let me look at the question. It says, is there enough evidence to reject the claim? And then if I go back, the first sentence, the researcher claims that the average wind speed in a certain city is 8 miles per hour. What is the rejection of is 8 miles per hour? Well, is would be equals. The rejection of that is not equals. Okay? So that's a not equals question. So making that a what? A left-tailed, a right-tailed, or a two-tailed test? Okay, good. Two-tailed, right? So it's two-tailed tests. So here, you're going to go ahead and put your normal curve. Well, no, I did that a step ahead. We'll just calculate the test statistic, which is z equals x bar minus mu over the standard deviation over the square root of n. Okay, so x bar is 8.2. Mu is 8 over the standard deviation is 0.6 divided by the square root of 32. Here we're going to have our solution is going to be 1.89 for our test value. So once we get our test value, then I'll draw my normal curve here. 1.89 is somewhere out here, so z-test is 1.89. Remember, I want to find that region because what is that called? Anything beyond the z-test would be called the p-value. But with keeping in mind, this is a 2-sample test. So if I get, right, if I do normal CDF, like I've been doing, second varus normal CDF of 1.89 to infinity, I get 0.0294. Okay. But what do I have to do to that? What do I have to do to that? Let's see if y'all remember. Times it by 2, right? So we would times that by 2, and then that's actually the p-value, because you'll notice on this problem that would make a huge difference, because if you didn't do it correctly, if you use this as your p-value, you would say it's less than, therefore less than alpha, and you would reject h naught. But if you do it correctly, meaning you take both sides of z-test into account by multiplying it by 2, then you actually get the p-value, well, which is 0.0587. So you would make the wrong conclusion. Okay, so that just be aware when you have a two-sided test and you're calculating the p-value, you're going to have to multiply whatever you get for normal CDF times 2. Okay, so that's one of those things you'll want to remember. Okay, so then from there, if my p-value is 0.0587, is that less than or greater than alpha? Well, that's greater than alpha. So we'd say something like since the p-value, is greater than alpha, we fail to reject h naught. That, and I'd just like to make a statement reminding us what that is, where the mean, oh, and look, now I just remembered. Okay, so that the mean defined would be where the true, where mu is the true population mean what? Wind speed. In a certain city. That's all it gives us. Okay, so that would be our defining of mu. And I referenced it over there, that's why I wanted to make sure I defined it. Okay, so here, now we make a statement about the alternative. If we fail to reject h naught, then what does that mean? No evidence for the alternative or evidence for the alternative? That means there is not sufficient evidence to suggest H1 is true. Okay. And let's just refer back to it that if you want to be consistent, mu is not equal to 8. Okay. Now, let's do something real quick. We said it was two-tailed. So, meaning let me take you back like 3 problems ago using the critical value method. So if we did inverse norm, just to prove it to you, right, alternate method, going back to the critical value method. So we did the p-value, so okay, so going back to the critical value, we would do step 2 would be the critical value, and we would do inverse norm of, since two-tailed, we'd have to do alpha over 2, so second varse inverse norm of 0.025, I end up with negative 2.05. So that'd be Z critical. Now don't get them mixed up. This is the cutoff point for the test statistic, which, remember that it's also going to be positive, right? Because it's two-tailed, 2.05. So it's two of them out here. So that it turns out that the Z critical would be somewhere out here, meaning under the critical value method, Z-test does not fall in the critical region. It does not fall in the critical region. Therefore, this would be the critical region, right? And then also over here on this side too, Z critical, because it's a two-tailed test. So since Z test does not fall in the critical region, we fail to reject the null hypothesis again, right? We come to the same conclusion, but for a different reason, since Z test did not fall in the critical region. Okay, but the main thing is, you know, you have the p-value method. All right, so just make sure you kind of understand those two. So moving on from that, there's slide 58. Says a couple of things. So just depending on your alpha, or if there is no alpha, right? If you just calculate a p-value and you're not given an alpha, so if you say the p-value is less than 0.01, the difference is highly significant. If the p-value is greater than 0.01, but less than between 0.01 and 0.05, the null hypothesis, the difference is significant, but not highly significant, but significant. So you see the levels. If the p-value is between 0.05 and 0.1, consider the consequences of a type 1 error, meaning you could reject when in fact the null would be true. Okay. But what about when the p-value is greater than 0.1? Do not reject the null hypothesis. The difference is not significant. Okay, so that kind of goes back to asking the question. So here there's not evidence to suggest that H1 is true. The alternative is true, meaning that the mean is different from 8, because it is, the sample is different. But remember the question: is it different enough to say that our null hypothesis is incorrect? And in this case, it's not different enough to say that based off our Z test and then calculating our p-value. It's not different enough to say there's evidence to suggest that our alternative is true, that the mean is actually not 8. So we would probably stick with, we failed to reject the null hypothesis. Okay. All right, so just consider those different p-values. Now also on the next slide, 59, the researcher should distinguish between statistical significance and practical significance. So not always, so if you have statistical significance, that doesn't mean it's practical. We'll talk about that, but when the null hypothesis is rejected at a specific significance level, it can be concluded that the difference is probably not due to chance and thus is statistically significant. However, the results may not have any practical significance. It is up to the researcher to use common sense when interpreting the results of a statistics test. So, moving on to 60, which that's the t-test. Okay, so here you have a different test. In other words, this formula on the test value for both the critical value and the p-value method would change using the t equals x bar minus mu divided by s over the square root of n. And remember, degrees of freedom is n minus 1. Okay, so when you're calculating your inverse t, you'll have to keep that in mind, because it'll ask you what's the degrees of freedom for your inverse t. Now, when do you use t versus z? Okay, if you look at that formula on slide 60, you'll notice that there's an s in place of the population standard deviation, and really that's the only difference other than t. So here's what's going to help you. If you're given population standard deviation a problem, you're going to use z like we've been doing. If not, you're going to use t, okay, when we're talking about means. Okay, so we'll look at a problem, but it also has a note there on the bottom of slide 60. When the degrees of freedom are above 30, some textbooks will let you use the nearest table value. However, in this textbook, you should round down to the nearest table value. So that's if you're using the table, but I like to use the calculator, which is going to be a little more precise than if you have to round the way they are suggesting. However, on slide 62, they do show you how to use a table. And different tables are different in their approach, but you know, they kind of have mostly the same idea. So this one's if you have a one. So if you have a one-tailed test, then you use the correct alpha, and then it'll give you the correct t score for. This would be for a sample size of 17 because the degrees of freedom would be 17 minus 1. Okay, on slide 62, which is from your table. But I'll let you look at that. I'm going to be talking about how to get it on the calculator, but again, you could always use the table or other software, right? There's plenty of ways you can get a t critical and a z critical. But right for now, I'm going to stick with using the calculator. Okay, so find the critical t value for alpha equals to 0.01 with degrees of freedom equals to 22 for a left-tailed test. Okay, so for a left-tailed test, let's go ahead and do this problem here. Okay, so on slide 64, they give you that alpha equals to 0.01 and degrees of freedom is 22. Well, just a side fact, that means the sample size would be 23. So you would want to use for your t critical. We're going to do t critical. It's going to be the inverse norm with area equals to 0.01, right? Because it does say for a left-tailed test. Right, so if you could imagine a picture, the area would be on this side. 0.01, we're looking for t critical this time. So the area would be 0.01, kind of same as before. If it's left area, it's alpha. Then your calculator will ask you degrees of freedom. It tells you here it's 22. Then that's it. That's all it'll ask you. So if you input that into your calculator, you should get t critical equals to negative 2.508. Okay, so that gives you that, and then from there we'll look at the next one. It says alpha 0.1 and degrees of freedom of 18, which that's a sample size of 19. So again, you're going to do t critical would be on this one was for a two-tailed test. Two-tailed. Okay, so you imagine the areas on both sides for your alpha, so that means this is 0.05, that would be alpha over 2, and then this is 0.05, that's alpha over 2. So now, if you remember for a two-tailed, you're going to input alpha over 2, but your degrees of freedom would now be 18, whereas before it didn't really ask you for degrees of freedom. So if you do that, you're going to end up with t criticals of negative 1.734 and positive 1.734. There's two t criticals because it's a two-tailed test. Okay. All right. So let's do a problem here about hospital infections. So let me just erase this. Okay, and actually before I do the problem, let me just kind of emphasize what I just did. For some reason, again, finding t criticals and z criticals is challenging for students. All it is going to be is inverse norm or inverse t. Okay, so practice that. Make sure you know how to do the left area, which is alpha, the right area, which would be 1 minus alpha, and then also the two-tailed, which would be alpha over 2, and then those would have two critical values, the positive and the negative. Okay. All right, so let's do the hospital infections. A medical investigation claims that the average number of infections per week at a hospital in southwestern Pennsylvania is 16.3. A random sample of 10 weeks had a mean number of 17.7 infections. The sample standard deviation is 1.8. Is there enough evidence to reject the investigator's claim at alpha equals to 0.05? Okay, so here step 0 is, again, very important. And now even more so because the questions are changing ever so slightly. You may not even noticed how it changed, okay? But it's slight, not much of it, but there's one part, but we're gonna get what we know, okay? So the 16.3, that's the claim number of infections, okay? Then you have your N was a sample of 10, okay? And according to that, 10 weeks. The mean number of infections, would be from that sample, so that's a sample average, it's going to be 17.7. And then what about the 1.8? What about the 1.8? You notice it says sample, right? So that's not the population standard deviation, it's a sample standard deviation, therefore it's S this time, which is going to be new for us from what we've seen in the previous ones. So, and then alpha is 0.05. So really nothing changed other than S, but what does S tell us, or what is the fact that we don't have the population standard deviation tell us that we're going to use? We're going to have to use the T formula, okay? All right, so we're going to do the critical value method. So step 1, the hypotheses. And again, still don't think too hard here. It's basically the mean. The alternative is going to be, we'll read the question one more time. Is there enough evidence to reject the investigator's claim? And we'll go back to the top, see the claim. A medical investigation claims that the average number of infections per week at a hospital in the southwestern Pennsylvania is 16.3. So the rejection of that is not 16.3. Not 16.3. So step 2, we would go ahead and find the critical value. Okay, so this is a little bit different too, because I'm using a T eventually, I need to find a critical T. So what does this mean? I'm going to draw my picture here, like we were doing on the critical value method. This is a two-tailed test. So that means this is going to be alpha over 2 at 0.025, divide that by 2. Same over here, 0.025. And then I want to get T critical. T critical, okay? So don't make it challenging. I mean, it's just basically you can do inverse T, okay? Of what the two-tailed, which is alpha over 2. So I'm going to do inverse T, and I'll write it to 0.025, and then you'd have to input the degrees of freedom. And I could also write that up here, which is going to be 9. It's just one less than the sample size. So when you do inverse T, it's going to ask you for an area. Of course, you're going to tell it 0.025 because it's two-tailed, and it's going to ask you degrees of freedom, and then you're going to write 9 because it's n-1. And then if you write that, you paste it, that's it, you get it. So it's negative 2.26. So that's negative 2.26 and positive 2.26 for the T criticals. Okay. All right, so those are my T criticals. Then I'd want to calculate my test value. Okay, and I haven't been changing up the color here, so apologize. So the test value here, again, because I have S, I knew I was going to have to do the t-test here. So hypothesis t-test. So here I'm going to do x bar minus mu over S divided by the square root of n. So this would end up with 17.7 minus mu 16.3 divided by S, which is 1.8, divided by the square root of 10. Okay, divided by the square root of 10. So here, I would calculate a number, and we'd report. Okay, and so what I get is 2.46. Okay, so that's 2.46 as my t-test, and then actually up here, yeah, we labeled that correctly. T critical would be positive and negative 2.26. Okay, so now we would go back and we would place t-test appropriately, or just determine it is t-test in the critical region. It turns out that's t-test because 2.26 is t critical, so that means t-test is in the critical region. Therefore, we can make our conclusion just like before. So this would be our step 4, our conclusion based on our our null hypothesis, since t test is in the critical region, we reject h naught that mu equals 16.3. Okay, and then of course I gotta, okay, it's okay if you forget stuff as long as you remember to go back and put it, where mu is the true population mean, what are we talking about here? Infections. And then do they tell us which hospital? At a hospital. At the hospital. They just said at the hospital in Pennsylvania, but it's a hospital. Okay. So then that's the conclusion for H naught. I would want to make a conclusion for step 5, or a statement summarizing what we would say about the alternative. So since we reject the H naught, is that evidence to support the alternative or not? There is sufficient, yeah, you know, I haven't used that one, but you can use that too. There is sufficient evidence to suggest H1 is true. That the mean number of infections in the hospital is not 16.3. Okay, so you see 17.7 is pretty close to 16.3, but statistically we were able to figure out that it's actually different. Okay, it's actually different. Okay, so that's all we'll say about that, and we'll do one more, then that'll have to be, we're going to skip the last one. Okay, it'll be on the side, but it's pretty much the same ideas. Okay, so this one says that you have, according to payscale.com, the average starting salary for a nurse practitioner is $79,500. A researcher wishes to test the claim that the starting salary is less than $79,500. A random sample of 8 starting nurse practitioners selected and their starting salaries are shown. Is there enough evidence to support the researcher's claim at alpha equal to 0.1, assuming the variable is normally distributed? Okay, so we're going to erase all this. Now, and we're going to go ahead and write our, what we have, okay, step 0. So the 79,500, that's according to payscale.com. That's a previously known fact. Okay, so that's what we're going to make our assumption, that's the mean. Okay, and we're going to test against that. So a researcher wishes to test the claim that the starting salary is less than 79,500. A random sample of 8. So that's going to be our N, which degrees of freedom would be 7. I'll just write that in. And then that's really it. They gave us the data. Okay, so is there enough evidence to support the researcher's claim at alpha 0.1? Okay, I'll put that. So I don't have X bar and S in this problem. So what am I going to have to do? Well, we're going to have to input those values. So which I'm going to go ahead and get right now. So S, if you input these into the calculator, you know, stat edit, you end up with enter the data, and then stat calc 1 bar stats will give you both of these real fast and efficiently. So 6,937.68. Okay. So those are those two numbers. Okay, but we'll come back to those. So first we're going to get the hypotheses. Again, I always say don't think too hard here. The mean is, or the null hypothesis is just your population parameter there. $79,500. The alternative, we know the number is going to be the same and the variable is going to be the same, but we want to determine if it's less than, greater than, or not equal to So is there evidence to support the researcher's claim? The claim being on the second sentence, a researcher wishes to test the claim that the starting salary is less than. Okay. So for less than, on the critical value, if I imagine my alpha is 0.1, right? So then I need that critical value, that t critical, right? Because I already know, how do I know it's t? Because I have an s here. I don't have a population standard deviation. Here's an interesting thing. If you have both, right? What if you have both this and s? What would you use? You'd have to use the z-score if you're given the population standard deviation. Okay, so that's a fun fact that might come up for you. But okay, so we're going to do inverse t. Inverse t, area, it's left area, so it's just area of alpha, 0.1. Okay, again, get really good at that, because I think that's where we might struggle the most. Area 0.1, and then you do degrees of freedom of 7, and then calculate that. Okay, so then you get negative 1.41 as your t critical. And then your positive t critical would be 1.41. Okay, so then your test value would be x bar minus mu over the standard deviation divided by the square root of n. X bar, what we calculated was 75,150 minus mu, which is 79,500 over s, 6,937.68 divided by the square root of n, which is 8. Okay, input that into a calculator and we should get an answer, and I get negative 1.773, which is the t-test. Okay, t-test. This would be t critical. And again, important to distinguish those so that we don't get them confused. T critical is the cutoff. T-test is the test, right? So that's we're gonna put it here. That would fall in the critical region, so it's negative 1.773. So our conclusion would be, since t-test falls in the critical region, we reject h naught, that the mean is equal to $79,500. Okay, and of course, you know I was going to forget that. Where mu is the true mean. Oh, let's see. Sometimes I forget what we're talking about. Nursing salary. True mean nurse's salary. Okay. And then so finally, step 5 would be that the statement H1, okay, is, so since we failed to reject, since the t-test falls in the critical region, we reject H naught. So since we reject H naught, that is, there is sufficient evidence to suggest H1 is true. Okay, and then the final thought here is that we could do, again, the rest is more the same, but the final thought here is that using the t-test, I can do normal CDF and get this area, and then do the same on the other side, or multiply by 2. So in other words, negative infinity, I'm going to do it normal CDF. I'm just going to verbalize it. Normal CDF, negative infinity to negative 1.773, negative 1.773. Well, let me make sure. Actually, okay, here's an interesting TCDF. Why? Because we're using t, not normal curves. So TCDF, negative infinity to negative 1.73, 73 degrees of freedom you have to input on TCDF that you don't have to on normal CDF, and I end up with 0.0597. So the p-value would be equal to 2 times 0.0597, or 598. Okay, so I would times that by 2, and then I get 0.1195, which the p-value is greater than alpha. And if you go back to that slide, I think it was 47, it says if the p-value is greater than alpha, you reject H naught, just like we did. So the results coincide, okay? So that would be the p-value method. You move step 2, remember, just go back to that slide. Step 2 for the p-value method was test value. Step 3 would be the p-value, which that would be step 3. And then step 4 would be you'd reject because the p-value is greater than, or actually, p-value is less than. Yeah, okay, so let me look at this one more time. Okay, so, like I said, it's okay if you make mistakes, you just got to find them. I got the p-value, and in fact, this is correct. That's greater than alpha, so you would fail to reject the no. That kind of told me there's something up with this, which goes back to our t-critical. Okay, so what I should have input was alpha over 2 because it's two-tailed, okay? Which I think I said, well, I'm not sure, but I didn't do. So this is what you should have done, inverse t. That's really the only correction, and if you do that, you end up with negative 1.89, which changes t critical, okay, 1.89, and nothing else really changes other than your t-test. So your t critical would be here. Now, let me just redraw this picture. Okay, your t-critical, we'll just say it would be here and here. 1.89 would be that, and then their t-test would actually fall within that, not your t-test with this time. Yeah, so that would be different as far as the t-test goes. Therefore, it is not in the critical region. So we just got to change one word here. Since t-test falls in the, or since t-test doesn't fall, test doesn't, does not fall. We'll do that. Couple words. Does not fall in the critical region, we fail to reject H naught that mu equals 79,500. Okay, so now that confirms this, and then there is not sufficient evidence. Not sufficient evidence to suggest H1 is true. Okay, so yeah, so you can see it can get a little bit messy. All right, well, I went a few minutes past what I wanted to, but don't worry, I'm not going to charge you. It's free. I will see you in class next week. This should help you with the homework. All right.